We have seen that to form an image of an object, all the rays coming from a single object point need to end up in a single image point. One might think that if we arrange a series of lenses in such a way that this condition is satisfied, we have basically completed our imaging system. However, there is another element that plays a very important role in imaging systems, namely the aperture stop. This aperture stop determines which cone of rays that comes from an object point will reach the image plane. Why would such an element be so important for imaging systems? In the following, we will discuss 3 reasons why aperture stops are relevant. The first reason is that an aperture stop can help reduce the impact of aberrations, which improves the image quality. The other 2 reasons have to do with the through-focus behavior of the imaging system. By this we mean how the image changes as we move the screen or detector back and forth with respect to the image plane. One property of the imaging system is how the resolution changes as a function of defocus. If the detector is in the image plane, then the image is sharp. As we move the detector out of focus, the image becomes blurred, so the resolution decreases. The depth of focus of the imaging system tells us how quickly the resolution changes as a function of defocus. Another property of the imaging system is how the magnification changes as a function of defocus. As the screen moves out of focus, then the magnification of the image may change, while at the same time the resolution decreases. In the case of a completely telecentric imaging system, the magnification remains constant as you move the screen out of focus. So let's see how an aperture stop may help reduce the impact of aberrations. In a perfect imaging system, all rays coming from a single object point end up in a single image point. However, in the presence of aberrations, different rays might intersect in different planes. This means that a single object point becomes a broadened spot on the detector, which means that the image of an object becomes blurred. By inserting an aperture, we can block the rays that focus in the wrong plane, and we are left only with the rays that focus in the detector plane, which leads to a sharper image. However, we should keep in mind that this line of reasoning is only valid in the ray model of light. When we consider the more accurate wave model of light, we have to take into account the effects of diffraction. Due to diffraction, a single object point can at best be focused into an airy disk, whose width is proportional to the wavelength of the light divided by the numerical aperture of the imaging system. So if we reduce the size of the aperture stop, the numerical aperture of the imaging system decreases, so the airy disk becomes broader, which means the image becomes more blurred again. So when the aperture stop is fully opened, the image may be blurred due to aberrations. By reducing the size of the aperture, we may reduce the effect of aberrations, which leads to a sharper image. But if we make the aperture too small, then the image gets blurred again due to diffraction effects. Now let's see how an aperture stop affects the depth of focus of an imaging system. The imaging system focuses the rays from an object point into a single point in the image plane. If we move the detector away from the image plane, we see that the rays are spread out over a spot, which blurs the image. If we introduce an aperture stop, we make the cone of rays narrower, which means it spreads out less quickly as the screen moves out of focus, so the image is blurred less. This means that the depth of focus is increased when we make the aperture stop smaller. So if we take a picture of objects at different distances, then we can increase the number of objects that are in focus by reducing the size of the aperture stop. Finally, let's see how the position of the aperture stop affects the telecentricity of an optical system. First, let's assume that the aperture is placed in a 2-lens imaging system, such that it is in the back focal plane of the first lens and in the front focal plane of the second lens. Such a system is sometimes called a 4F system, or a telescopic imaging system. Now let's see what happens to the cones of rays from different off-axis point sources. The central ray of the cone is called the chief ray. Since the aperture stop determines the cone of rays that travels through the imaging system, the chief ray of a certain point source can also be defined as the ray that goes through the center of the aperture stop. Since the chief rays go horizontally through the image plane, the magnification of the image remains constant as the detector moves through focus. Such an imaging system is called telecentric. Now let's see what happens if we shift the aperture stop. We see that for the off-axis point sources, the cones of rays don't travel horizontally anymore through the image plane, since the chief rays aren't horizontal. This means that the magnification of the image changes as the detector moves out of focus. So if we have two objects at different distances, then in a non-telecentric system, the images will have different sizes, whereas in a telecentric system, the images will have the same size.